Welcome to the lectures on digital control systems. Firstly, we would try and see why digital control systems is required when we have a lot of analog control systems. First, the thing is, what is the motivation for digital control systems when we are having analog control systems? The motivation here is, with the advent of digital computers, which are cheap and which are highly flexible and which are high performance devices, and with the advent of microprocessors and microcontrollers, all these three different systems help us in solving the complex problems easier which we have faced in analog control systems. So this is the various advantages in going for digital control systems. Before going into this digital control systems, we will also try and see what are the various, when you study about digital control systems, any digital control systems will be dealing with continuous time signals and discrete time signals. Any digital control system is not purely digital control. It is continuous time, it is making use of continuous time signals and discrete time signals. So we need to understand what are the various types of signals that we are going to come across when we are working on digital control systems. So the various types of signals that are existing for us are continuous time signals, then continuous time analog signals, or you can call it as analog signals directly without any problem. The third one, the sample data signal, discrete time signal, and digital signal. These are the various signals that we are going to study when we are dealing with various types of signals that we are going to study when we are dealing with digital control systems. So firstly, let us try to differentiate what are the various types of signals and how they are behaving when you are treating them in the various systems that we are going to see. The first thing we will see, the continuous time signal. Continuous time signal is defined as a signal that is having values for continuous range of values of time. That is a simple definition. You can also see here, if f of t is our signal, let me say if we have a certain signal of this shape which is running from 0 to time, as time t is tending to infinity, you can have this continuous time signal. Now, this is a continuous time signal, and I would like to introduce this term, quantization. Quantization is nothing but having any signal f of t having values at discrete instants of time. Or you can say, for example, the same signal, when I am having it like this, the same continuous time signal which I have considered here, if I am taking it like this, now if I quantize amplitude, for example, let me say if I am dividing the amplitude equally, then this is called, at every instant of time you will have certain values of magnitude. Then this is called amplitude modulation or amplitude quantization, and quantization will have different values of time, different values. F of t will have different values, and these values are called quantized values. These values are called quantized values. Or in continuation to that, I can say I have values of this signal like this. Probably from that diagram, if I can get this diagram like this is a continuous time quantized signal. For every value of time you will have some value, but during this period the value is the same. It is quantized, the magnitude is quantized. For this time period 0 to t1, let us say, and for t1 to t2 it has got one particular value, and it is t2 to t3 it has got one particular value, and t3 to t4 it has got one particular value. So we will have this as, this can also be called as f of t, and this is continuous time quantized signal. So you can say analog signal, continuous time signal is having a broader sense, when you are going with broader sense compared to the analog signal. That is the only difference between analog signal. An analog signal is a special case of continuous time signal. Is a special case of continuous time signal. Now we will go and look into the third part of third type of signal which we are having. This is the sampled data signal. Sampled data signal. I will consider the same example again here. If I am having a signal, continuous time signal like this, now I would like to sample this signal. That is, it is divided, the time is divided into various parts of equal time quantum. You can say at this point, at 0 time, I have this value. At time t is equal to t, the magnitude of f of t is so much, and at time t is equal to 2t, the magnitude of f of t is so much, and at 3t, 4t, 5t, and so on. So you can see that if I erase this, you can have a clear picture of the sample data signal. It is somewhere related to the continuous time signal which we have taken as an example. Now this is called a sample data signal. That is a signal which has values only at discrete instance of time. That is called a sample data signal. Now you may ask, we are losing certain information in between any two instances. You are losing certain information in between any two instances. You can see that we have lost so much information, right? So in order to eradicate or minimize that effect, you will reduce the value of time, time or the sampling period t is the sampling period. We will see this in our later classes. T can be reduced as much as possible, and since sample data signal is a part of a digital signal, you can say that you can always reduce the value of time, which is, we are working on digital computers or microprocessors or microcontrollers of these signals. Therefore, the time period t can be reduced to a very minimum extent, so that in the order of nanoseconds or in the order of picoseconds, so that you will not lose much of information, because the time period between any two instances will be as much less as possible. Therefore, we will not lose much information when you are going with very small time period. This is about sample data signal. Now we will see digital signal. A digital signal is a combination of both sampled signal and a quantized signal, time quantized signal. Amplitude, a digital signal is both time and amplitude quantized. Time and amplitude quantized. That is, it is in the form of binary words. It is in the form of binary words. That is in the form of 000, 001, 010, 011, 100, 101, 110 and 111 if you are taking a 3-bit word, right? So this represents a 0, this is 1, this 2, 3 and so on. This represents these values. So every bit is considered, every value is considered, and so digital signal can be, any analog signal can be converted into digital signal easily when you are going for time quantization and amplitude quantization. The diagram for this may be of this form. F of t. I will take the same example again. If we are having the same continuous time signal, now what we try to do is we try to divide this into equal number of parts, 2t, the time axis into equal number of parts, that is time quantization, 5t for example, and I will also try to divide the amplitude equally so that I will get. Now I have this value, this is 000 and this is 001 and this 010, 011 and 100 and above which. Now what I try to do is, this is the value at time t is equal to 0. What is the magnitude that we have here? It is here, right? When we will just, what the digital signal, how we get the digital signal is, we will see this value whether it is nearer to 001 or nearer to 010. So we approximate this signal. So a digital signal is an approximation. Always a digital signal is an approximation. You will not get the actual signal because you are going to lose a certain part of information until and unless you are reducing the value of time and you are reducing the amplitude modulation here. The difference, the distance between any two magnitudes, if you cannot reduce it and if you cannot reduce time, the time period or the time sampling period, then you will lose a lot of information here. That is why we call this as an approximation, and because this is nearer to this, I will approximate the value here. Now this is going through this signal, we don't have any problem. Now this signal is going via this one, so I will approximate it to the nearest value. Now this is at the nearest value and this is here and this is here. So we have these values, and if I try to erase these values, you can have this you can see the picture, clear picture of the entire digital signal. So I have this here, 001 here, 0 1 0 0 1 0 0 0 0. At time t 2t it is 1 0 0. Again at 3t it is 1 0 0. At 4t it is 0 1 1, and at 5t it is 0 1 0. So this is a digital signal. It is having 0, it is 2, right? You have likewise you have various values. Now this is a digital signal. It is converted. A continuous time signal is converted into a digital signal in the form of binary words. Now we all know digital computers, microprocessors and microcontrollers work on only zeros and ones. Now we have the digital signal. An analog signal or a continuous time signal is converted into digital signal without any problem. Now you can use this signal in the digital computer and you can process the signal and get back an output which can be sent as a control action to the actuator of the plant. Now as a part of this, we would like to understand what is the block diagram of a digital control system. Before going into the block diagram of a digital control system, I'll try to just recap what is the block diagram, what are the various parts in an analog control systems. Suppose we have a plant here or the system or the process, we require a desired output y of t. This is our output, desired output. And the plant is actuated by an actuator which runs or drives the plant. There are the actuator dynamics that run the plant, and here we apply the controller. This is the analog controller, and here we have the error signal and the reference signal, a transducer or a sensor, which is coming from the output. The feedback from the output is fed back to the reference signal and you get an error signal which is processed. This error signal is processed in this analog controller, and this signal, a control action U of t, is given to the actuator which drives the plant, and you get the desired output in an analog control systems. Now, what is the basic difference between a digital control systems and an analog control system? This is the difference. The rest of the linear control systems or the analog control systems remains the same. You have the plant as such, you have the actuator as such, you have the transducer sensor as such, and you have the input as such. Everything remains the same, but you only replace an analog controller with a digital controller in a digital control system. So you are going to work on the digital control part, where you are going to see how you can replace an analog controller with a digital controller. So we are going to look into this part of the digital controller. So we'll see a block diagram of digital control systems. I'll start from this point. This is our output C of t, which is an analog value. We require an analog signal because all our instruments, all our plants, or whatever signal we require only analog counterparts of the digital signal. So analog output is desired analog output, which is obtained from the plant. This is the plant, and an actuator is always there for the plant to work properly. Then they have the analog, the dynamics of the actuator there, and here from this point on we require. Now this is also an analog signal. This should also be an analog signal. Now from this point we have the controller part. From this point we have the controller part. We will see what are the various parts of a digital controller. Digital controller basically consists of, like we have discussed initially, a digital computer. Without a digital computer, you cannot process any digital signal. Now, what is the output of a digital computer? It is a digital signal. The output of a digital computer, it is a digital signal. So, any digital signal you will have to convert it into an analog signal for us. So, digital to analog converter is required, and a zero order hold. We will discuss what is zero order hold in our later classes, right? Which will try and help us in reconstructing the analog signal. The output of a zero order hold will always be an analog signal, right? So we have digital signals here, and now what should be the input to the digital computer? We require an digital signal again. But here, what are we having? We are having a reference signal R of t and a feedback. A summer is given here so that it can measure a transducer or a sensor which is coming from the plant. You can also place a disturbance signal here. Disturbance or a noise signal. You can also place some signal here, which doesn't matter much for us now at this point of time. Now a digital signal is required. When you require a digital signal, what is required? You require an analog to digital converter. That is, you require a sampler. A sampler and an analog to digital converter you require. Now this is an analog signal. Here you have the digital signal, and this is our error signal, which is again an analog signal. Right. So this is our analog signal or a continuous time signal. This is our reference input. This is also an analog signal. Okay, because you are having a digital analog output. This is a digital signal, this is an analog signal. The disturbance is again an analog signal. It is continuous, it has got values for various continuous values of time, and this is an analog signal. Everything here external to this. So this is our digital controller. Digital controller. Now to synchronize all this, we require a clock. To synchronize the analog to digital converter and digital to analog converter, we require a clock which will sample and convert. Sampling process and conversion process takes place in this digital computer with the help of this clock. The synchronism between analog to digital conversion and digital to analog conversion will be controlled by the clock. Otherwise, if there is a delay in analog to digital conversion and digital to analog conversion, one signal will be representing at some other time, so the signal will get distorted. So you should have a clock here to synchronize the analog to digital conversion and digital to analog conversion in this stage. So this is the entire block diagram of a digital control systems. You can see an analog input and you can get a desired analog output. So any analog control systems or digital control systems, the input and output both are analog signals. Only in the digital controller that we are using, in this part where you are using digital computer, you are having a digital signal, and here for conversion from analog to digital you are using an analog to digital converter plus a sampler. and for digital to analog conversion you are using a digital to analog converter plus a zero order hole to reconstruct back an analog system, analog signal from the digital signal.